Hi students, today I have come up with one more important topic from the chemical bonding, that is molecular orbital theory, MOT, molecular orbital theory. This molecular orbital theory explains the limitations of the valence bond theory. So whatever the limitations are there in the valence bond theory, this theory explains all those limitations. Okay. So here what are the limitations of the valence bond theory? First we will briefly discuss that one. So here first one here, it does not explains the chemical bond formation. So here it does not explains chemical bond formation in molecules. Here valence bond theory does not explains the chemical bond formation in the molecules, and also it fails to explain the bond strength of the molecule. And the third one, magnetic properties. And the fourth one, color exhibited by the molecules in visible light. So here all these are successfully explained by the molecular orbital theory. So here, molecular orbital theory explains you about the chemical bond formation in the molecules, and also it explains you the bond strength and magnetic properties. Magnetic properties, here two types of magnetic properties we'll discuss here: diamagnetic property and paramagnetic property. First here, paramagnetic. If any molecule contains unpaired electron, we can say the molecule is paramagnetic. If there is no unpaired electron, that is diamagnetic in nature. Okay, if unpaired electron is there, that is attracted towards the magnetic field, paramagnetic. And if diamagnetic means if no unpaired electrons are there, they are repelled by the magnetic field. Okay, so because of the unpaired electron, they exhibit color. Paramagnetic, they exhibit color. And diamagnetic, no unpaired electron, that is diamagnetic molecule. So magnetic properties and the color, all these properties are successfully explained by molecular orbital theory. So here now we'll discuss what are the postulates of MOT, molecular orbital theory, briefly. Okay. Now postulates of MOT. So first postulate. Here atomic orbitals, atomic AOs means atomic orbitals. Here the first point in the molecular orbital theory is atomic orbitals combine to form molecular orbitals. First point. Atomic orbitals combine to form molecular orbitals. So here, when the atomic orbitals are combined for the bond formation, when the atomic orbitals are combined, two or more atomic orbitals, when they combine to form the molecular orbitals, they lose their identity and forms a new orbitals. Got my point? Here, when the atomic, first point is atomic orbitals combine to form molecular orbitals. That is means atoms combine to form molecules. So atomic orbitals combine to form molecular orbitals. And after that, here, when the atomic orbitals are combined for the bond formation, these atomic orbitals lose their identity and forms a new orbitals. Those new orbitals we call as molecular orbitals. What is the first point? Here, when the atomic orbitals combine for the bond formation, they lose their identity and forms a new orbitals. Those new orbitals are called as molecular orbitals. What are they? MOs means molecular orbitals. First point, atomic orbitals combine to form molecular orbitals. Okay. Second point, here, number of atomic orbitals combined is equal to number of molecular orbitals formed. Got this point? What is the second postulate of this molecular orbital theory? Number of atomic, if how many number of atomic orbitals are combined, here the number of atomic, if 2 atomic orbitals are combined, 2 molecular orbitals are formed. Okay, so number of atomic orbitals combined is equal to number of molecular orbitals formed. This is the second postulate. This is the second postulate. And the third point is here, these, when the atomic orbitals are combined, it lose their identity and forms new orbitals, those we called as molecular orbitals. That is the first point. And number of atomic orbitals is equal to number of molecular orbitals formed. Okay, and the third point here is when atomic orbitals are, if for example, if 2 atomic orbitals are combined, 2 molecular orbitals are formed. Okay, and the 2 orbitals, one is of here, if the 2 atomic orbitals are combined, for example, let us assume 2 atomic orbitals are combined, forms 2 molecular orbitals. Those 2 molecular orbitals, one is of lesser energy. The new molecular orbitals, among the 2 new molecular orbitals formed, the one molecular orbital is with lesser energy, and another one with higher energy than this atomic orbitals. Okay, so here if 2 atomic orbitals are combined, resulting in the formation of 2 molecular orbitals, one molecular orbital is with lesser energy than the atomic orbitals, original atomic orbitals. That lesser energy molecular orbital we call as bonding molecular orbital. Bonding molecular orbital, and the one with higher energy than the original atomic orbital is called as anti-bonding molecular orbital. Got this point? Bonding and anti-bonding molecular orbitals. Here, anti-bonding molecular orbitals we represent with a star. Okay, so here try to understand this point clearly. So here here what is our second point? Number of atomic orbitals combined is equal to number of molecular orbitals. So here if you assume if 2 atomic orbitals are combined, so let us assume if 2 atomic orbitals are combined, for example, you take one hydrogen 1s1 and another hydrogen, second hydrogen 1s1. Here, what is the electronic configuration? 1s1, 1 electron. Here, this is one atomic orbital and this is the second atomic orbitals. I told you, no, 2 atomic orbitals combined to form a molecular orbitals. 2 molecular orbitals, 2 atomic orbitals. So, resulting will be 2 molecular orbitals now. So, the one with lesser energy than this one, that is bonding molecular orbital, and the another molecular orbital is higher energy than this one, that is known as anti-bonding molecular orbital. So here 1, 2. This is bonding molecular orbital, and it is anti-bonding molecular orbital. Clear? So here the 2 atomic orbitals, okay, this is the energy axis. So the 2 atomic orbitals combined 2 molecular orbitals. Among the 2, one is with lesser energy called bonding molecular orbital. Lesser energy than what? Lesser energy than this atomic orbital. Less energy than this one. Less energy than this one. High energy than this one. So high energy is anti-bonding molecular orbital and lesser energy one is called bonding molecular orbital. If here you write down one point. If the electrons are present in the bonding molecular orbital, that molecule is more stable. Okay, I'll discuss that point later. Just you try to write a note or just try to remember that point. Okay, so this is the third postulate. Clear? Then Next point. Now, the next postulate is here, fourth one. When atomic orbitals are represented by s,p,d,f orbitals, like that, as the atomic orbitals are represented by these s,p,d,f, the molecular orbitals are represented by sigma, pi and delta. So here bonding molecular orbitals with sigma, pi, delta, like that, and anti-bonding molecular orbitals sigma star, pi star, delta star, like that. This is anti-bonding molecular orbitals. This is the next point you have to remember. As the atomic orbitals are represented by s,p,d,f, you know that molecular orbitals, here the atomic orbitals are combined to form molecular orbitals. Now how to represent that molecule and how to write the electronic configuration? So here the molecular orbitals are represented by sigma, pi, delta. Here delta is not in your scope. So here mainly we use sigma and pi here. So sigma, pi bonding molecular orbitals, and anti-bonding molecular orbitals, I told you, we represent with a star. Okay. So these molecular orbitals are represented like this. And how to write the electronic configuration? Fifth point. To write the electronic configuration, we follow the same rules. What is the rules here? Aufbau's principle, Hund's rule of maximum multiplicity, and Pauli's exclusion principle. So here electrons are filled in this bonding and anti-bonding molecular orbitals by following these rules. Okay, that is the next point. Here atomic orbitals combine to form molecular orbitals. First point, a number of atomic orbitals formed combined is equal to number of molecular orbitals are formed. If two atomic orbitals combined, we get two molecular orbitals. One is with lesser energy, another one is with higher energy. Lesser energy we call as bonding molecular orbital. Higher energy one we call it as a. Here I showed you by drawing a diagram also, like that. Bonding and anti-bonding. And how to represent? Here as the atomic orbitals are represented like s,p,d,f. Likewise, here molecular orbitals are represented. Bonding molecular orbital sigma, pi, anti-bonding molecular orbital sigma star, pi star, like that. And here how to fill the electronic configuration. While writing the electronic configuration for the new molecular orbitals, we follow these rules. Aufbau rules, Aufbau's, Hund's and Pauli's exclusion principle. Okay, just you recall what is Aufbau principle, Hund's rule and maximum Pauli's exclusion principle. What is Aufbau's principle? Here, filling of electrons takes place in the increasing order of their energy. Filling of electrons takes place in the increasing order of energy. And Hund's rule, what is Hund's rule? Here, pairing of electrons starts in the degenerate orbitals. Means here you take this p orbital. Okay, so for example, how we fill the atomic orbitals? For example, we have 4 electrons. We have to fill 4 electrons. So here in atomic orbitals, here I am saying in the atomic orbitals, first electron, second electron and the third electron. Here Aufbau's principle, electrons are filled in the, here if s orbital is there, first we will fill that one. So pairing starts in the increasing order of their energy, s, p, and after that second point, Hund's rule. Pairing of electrons starts in the degenerate orbitals. Here p orbitals means here px, py, pz, all the 3 are degenerate. Means same energy. So here pairing in the degenerate orbitals starts here after. When will start pairing? one electron for each orbit. Means px one orbit, py px one electron, py one electron, pz one electron. So next fourth electron. Okay, pairing starts in the degenerate orbitals. This is Hund's rule. Pairing starts in the degenerate orbitals after each orbit gets one electron each. So here, like that, here the pairing of, for example, it is pi 2px is equal to pi 2py. I'll explain this later. Otherwise, okay, leave it. So here, what is Pauli's exclusion principle? No two electrons in an atom can have same set of 4 quantum numbers. So here, this should be like this. Pairing, the spin should be opposite. Okay. So here, while writing the electronic configurations, we went to atomic structure. Of Bose principle, electrons are filled in the increasing order of energy. Hund's rule of maximum multiplicity. Pairing of electrons in the pairing starts when each one of them will get a single electron. Okay. Pauli's exclusion principle, the electrons should be in an opposite spin because no two electrons in an atom can have same set of 4 quantum numbers. That is Pauli's exclusion principle. The important postulate you have to remember is here, this is the 6th postulate. Here in the first postulate itself, I told you atomic orbitals are combined to form the molecular orbitals. Now, how these atomic orbitals are combined? How these atomic orbitals are combined? That is here to explain this atomic orbitals here. The combination, how they are combined to form the molecular orbitals. Okay, try to get my point. How these atomic orbitals are combined to form the molecular orbitals, that was explained by LCAO approach. Linear combination of, linear, C means combination, linear combination of atomic orbitals. Here, how the atomic orbitals are combined to form the molecular orbitals. To explain that, they have adopted LCAO method, linear combination of atomic orbitals. According to wave mechanics, here each atomic orbital is expressed in the form of a wave function xi. Here it was expressed in the formation of a wave function. Each atomic orbital is expressed in the formation of a wave function xi. So here, what is the method they have adopted to explain the atomic orbitals combination? That is LCAO approach, linear combination of atomic orbitals, by considering atomic orbital, each atomic orbital as a wave function xi. For example, here, if the two atoms are combined, atoms A and B are combining, and the wave function of A is xi A, and the wave function of the atomic orbital B is called as xi B. So here, this is the wave, how the atomic orbitals are combined. That is, to explain that, the method is LCAO approach, linear combination of atomic orbitals, in which each atomic orbital is expressed in the form of a wave function. Okay, now we'll see. Here, for example, it is psi A. This is one atomic orbital wave function, and it is psi B. Okay, here, when they are add up, means when they are in constructive phase, we get one molecular orbital with increase in the amplitude. When they are, this is called amplitude, no? So when these two wave functions, here, when the two atoms A and B are combining, and xi A is the wave function of atomic orbital A, and xi b is the atomic wave function of the atomic orbital b. So here each atomic orbital is expressed in the form of a wave. I told you now. So here these two are combining. For example, they are adding up. Constructive interference we call. So if these two wave functions are in constructive interference, we get one molecular orbital. And the second possibility, if they are in destructive interference, means here if they are subtracted, the amplitude is less, no? Like this. We'll get another molecular orbital. So, if the two wave functions are in constructive interference, we call whatever the molecular orbital formed, that we call as bonding molecular orbital. If the wave functions are in destructive interference, we call it as a anti-bonding molecular orbitals. This is one of the important point I want to explain to you. LCO approach. Now coming to the electronic configurations, we have two electronic configurations according to molecular orbital theory, and first one is here, if the number of electrons are less than or equal to 14. If the number of electrons in a molecular orbital are less than or equal to 14, then the electronic configuration is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equal to pi 2py, means these two are degenerate. Okay, pi 2px is equal to pi 2py, sigma 2pz, pi star 2px is equal to pi star 2py, sigma star 2pz. If the number of electrons are less than or equal to 14, then we will follow this electronic configuration. If the electronic configuration is greater than 14, then the electronic configuration is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px is equal to pi 2py, pi star 2px is equal to pi star 2py, sigma star 2pz. No need to worry, here I will tell you, less than 14 L, less than 14 L, P. Okay, less than 14. If the electrons are less than or equal to 14, less than or equal to 14, here L less than, here pi orbitals comes first, pi 2px, Lalu Prasad. Okay, you remember like that. So here pi 2px equal to, here these two are degenerate electron, no, pi 2px is equal to pi 2py. So here next immediately here sigma 2pz, between the sigma 2pz and sigma star 2pz, anti-bonding orbitals of these two. Okay, and here if the electrons are greater than 14, then here first you write this sigma 2pz. Here between these sigma 2pz and sigma star 2pz, you will get pi 2px equal to pi 2py. Immediately anti-bonding orbitals of pi 2px and pi 2py. Okay, less than pi orbital will come first after the 2s orbital of anti-bonding orbital of 2s1. Okay, like that you remember this electronic configuration. Now we will solve some questions. Now we will discuss by using that electronic configuration how we can predict the bond order or bond strength, bond length and the magnetic properties, all these properties. Okay, first we will write the electronic configuration once again. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s less than 14 electrons. No, first we'll discuss that one. So less than, so pi 2px is equal to pi 2py, sigma 2pz, then pi star 2px is equal to pi star 2py, sigma star 2pz. This is the electronic configuration for if the number of electrons are in a molecular orbital are less than or equal to 14. So first here we'll explain we'll take hydrogen molecule. So here what is the, if one hydrogen molecule means here how many number of electrons? 2. So here what is the electronic configuration? It is sigma 1s2. Sigma 1s2. Now how to write the energy level diagram? 1s orbital of, this is psi of one hydrogen 1 and 1s orbital of another hydrogen 2. This is, you assume psi 1 and z2. Xi of H1 and Xi2 of H2, whatever it may be. This is one atomic orbital and another atomic orbital. Gives two orbitals. One is with less energy and another one is with more energy than this atomic orbital. Here one electron, hydrogen. These two combine to form a molecular orbital. So here this is sigma 1s2. It is sigma star 1s. So this is energy. Now by using this electronic configuration, here if you observe in the hydrogen molecule, here number of bonding electrons, I told you, no, if the electrons in the bonding orbitals are more when compared to the anti-bonding orbital, then the molecule is stable. So here hydrogen, it is 1s2. Okay. Now bond order. We have to calculate bond order. Bond order means which indicates bond strength. Okay. Here the formula to calculate bond order BO is equal to 1 by 2 into number of bonding minus number of anti-bonding electrons. NB, number of bonding electrons. Number of bonding electrons. Number of anti-bonding electrons. Number of anti-bonding electrons. So here what is the bond order for this hydrogen? NB minus Na, which is equal to 1 by 2. Now how many bonding electrons are there? 2. Anti-bonding 0. So bond order is 1. So bond order 1. Bond order, how to calculate bond order? Bond order is equal to 1 by 2 into number of bonding minus number of anti-bonding orbitals. Here number of electrons in the bonding orbital and number of electrons in the anti-bonding orbital. So here it is 1. Bond order 1 indicates that there is a single bond between two hydrogens. If bond order is 2, there is a double bond. If bond order is 3, there is a triple bond. Bond order even may be a fraction also, 0 also. Okay, it may be 0 or a fraction. So bond order which indicates the strength. And here if here bond order is next one, it is the bond length. Now bond length is inversely proportional to bond order. If the okay, and next bond length and bond order both are inversely proportional to each other. Now I'll write one here. Bond order is equal to 1 by 2 into number of bonding and number of anti-bonding electrons. Bond order is directly proportional to stability. And here it is bond order and bond length both are inversely proportional. Okay. Now magnetic properties. And next one is magnetic properties. magnetic properties. So here, if number of unpaired electrons are there, that is paramagnetic. If there is no unpaired electrons, then the compound is diamagnetic. So here hydrogen molecule, no unpaired electron, so it is diamagnetic. Okay, and the magnetic moment can be calculated by the formula square root of n into n plus 2, where n is number of unpaired electrons, Bohr magnetons units. For the magnetic moment, it is Bohr magnetons, number of unpaired electrons. Okay, if there are no unpaired electrons, then the molecule is diamagnetic. Now hydrogen is diamagnetic. Okay, bond order is 1. Okay, and magnetic moment, it is n into square root of n into n plus 2 Bohr magnetons, where n is number of unpaired electrons. Okay, and now you write the electronic configuration and energy level diagram for this H2 plus. So for hydrogen, what is the bond order? It is 1 and it is diamagnetic. Next, H2 plus. H2 plus means how many number of electrons are there? Plus means total number of electrons minus 1. So here 1 electron. Okay. So what is the electronic configuration? Sigma 1s1. What is the bond order? 1 by 2. Number of bonding minus number of anti-bonding electrons. So here 1 by 2 bonding electrons 1 minus anti-bonding 0, 1 by 2, 0.5. I told you no. Okay. And for hydrogen, it is 1 diamagnetic. And what about the magnetic nature? 1 unpaired electron is there. It is paramagnetic. So H2 plus, here number of electrons. Here write this one. Here this is bond order for hydrogen. Now bond order for H2 plus. H2 plus bond order is, right here, bond order for H2 plus, it is 0.5 and it is paramagnetic. Okay. And next, you write for the H2 minus. Here 2 plus 1 electrons, altogether 3 electrons. So here what is the electronic configuration? Now you write the electronic configuration. 1s2, 1s1. So there is an electron in the anti-bonding orbital too. Now you calculate the bond order. Bond order is equal to 1 by 2 number of bonding minus number of anti-bonding. How many bonding electrons are there? It is 2 minus 1, which is equal to again 0.5. So for H2 minus, the bond order is 0.5 and 1 unpaired electron is there, that is paramagnetic. Now the question is, here I'll write one question based on this. Okay, so first you try to understand this one. I have taken hydrogen molecule and hydrogen plus molecule and hydrogen minus molecule. For all the three I have calculated bond order and the magnetic properties I have interpreted. Now tell me or write the stability order for hydrogen, H2 minus, H2 plus. Write down the stability order. Now write down the question. Compare the stabilities of H2, H2 minus, H2 plus. So here, first hydrogen molecules comes first because bond order is 1. For these two, bond order is 0.5. So first comes to hydrogen, most stable. Now among these two are having same bond order. Now how to decide? Here although the bond order is same and both are paramagnetic too because they contain unpaired electron. Now you look for in the H2 plus, here one electron is there and here there is no electron in the anti-bonding molecular orbital. So I told you, if anti-bonding molecular, if in the anti-bonding molecular orbital, if electrons are there, that is less stable. So here, which comes first? H2 plus and H2 minus. Here if you look at H2 minus, there is an electron in the anti-bonding orbital which makes that molecule less stable when compared to H2 plus. Although the bond orders are same, there is no electron in the anti-bonding orbital of H2 plus. But here there is an electron in the anti-bonding orbital of H2 minus. So among these two, H2 plus is more stable than last. This is the stability order for hydrogen. Clear? Super clear? So first you have to memorize this electronic configuration and the formula for bond order, 1/2 number of bonding minus number of bonding anti-bonding orbitals, and the magnetic properties. If no unpaired electron is there, diamagnetic. If unpaired electron is there, paramagnetic, like that. Okay? This is for today. Now here immediately I'll make another video by explaining examples. Okay? Till then, bye.